Alright, in this video we're going to be looking at maximum and minimum problems. And we're going to first look at, in Calculus 1, we had something called the extreme value theorem. And that says that if f is continuous on a closed interval AB, then f has both a minimum and a maximum value on the interval. So the procedure in Cal 1 was to locate the critical numbers of your function f. A critical number c in the domain of f is a number c such that f prime of c is equal to 0 or f prime of c does not exist. So if f prime of c is equal to 0, then that means you have a horizontal tangent. If f prime of c doesn't exist, but the value of the function is defined at c, then we could have a corner, we could have a cusp, or we could have a vertical tangent. So let's make up a graph here, or a function here, and let's say we have f of x is equal to x squared plus 2x, or sorry, just regular x, on the interval negative 2 to 2. The first derivative is going to be 2x plus 1, and then we're going to solve that equal to 0 to find our critical value, that is x to the minus 1/2. So there's no place where this function's undefined, so x is equal to negative 1/2 is our one critical number. Okay, once we've done that, we're going to evaluate the endpoints f of a and f of b, and evaluate all critical numbers f of c. The largest value is the maximum, and the smallest value is the minimum. Okay, so f of 2 is going to be 2 squared plus 2, which is going to be 6. F of negative 2 is going to be negative 2 squared plus 2, plus negative 2, that's going to be 2, and then your critical number, f of negative 1/2, can be negative 1/2 squared, and then plus negative 1/2, and that's going to be negative 1/4. So the maximum there and the minimum, so we have the minimum is negative 1/2 and negative 1/4, and the maximum is 2,6. And so we can do a rough sketch. Okay, so there would be our parabola right there, restricted to minus 2 to 2. Okay. Let's do another example where we have f of x is equal to x to the 2/3 power. The domain of that is all real numbers. However, when you take the derivative, you're going to get 2/3 x to the minus 1/3. And that's not going to be equal to 0, but f prime of 0 is going to be, well, it's not going to exist. And so that would be a critical value there. So then when we look for the extreme on the closed interval, we're going to check the endpoints, negative 2 and 2, and also our critical number of 0. So f of negative 2 is going to be negative 2 to the 2/3 power, so that'd be square and cube root, or we could say it's 4 to the 1/3 power. F of 0 is going to be 0 to the 2/3 power, which is just 0. And f of 2 is going to be equal to 2 to the 2/3 power, which is going to be equal to 4 to the 1/3 power. Most likely we looked at this in Cal 1, and so we might have said something silly. We called it like the seagull or something to that effect. Okay, and so that's what it's going to look like. It has a minimum at the origin, and then it has two maximums at plus and minus 2, and comma 4 and 1/3. All right, let's continue on to the next slide. Okay, so we have a theorem, the second derivative test. And the second derivative test says that if f prime of c is equal to 0, so that means you got a horizontal tangent, and the second derivative exists on an open interval containing open interval I containing c, then the first thing is if your second derivative evaluated at C is greater than 0, that means you have concave up, and so you're going to have a relative minimum at C comma f of C. If the second derivative was negative at C, then you have concave down at C, and you have a relative maximum at the point C comma f of C. If the second derivative evaluated at C is equal to 0, try something else. Go back to the first derivative test. All right, so if we look at f of x is equal to x squared plus x, f prime of x is going to be 2x plus 1. That's going to be equal to 0 when x is equal to negative 1/2. So then the second derivative of f is going to be 2, and so f double prime at negative 1/2 is equal to 2. That's greater than 0, and so by the second derivative test, that tells us that we have a minimum at this c comma f of c, so negative 1/2 comma f of negative 1/2. And on the previous slide, we said f of negative 1/2 was negative 1/4. Okay. So now we're going to go into 3 dimensions, and we're going to look at extrema. So let z equal f of xy be a function of 2 variables that is defined and continuous on an open set containing the point AB. Then f has a local maximum at AB if f of AB is greater than or equal to f of xy for all points xy within some disk centered at AB. Okay. So here's our point AB, and then the disk that it's centered in, and then we have our point f of AB. So if we have any other point, x comma y, and then f of xy, f of AB is going to be greater than or equal to f of xy. Okay. All right, continuing on, the number f of AB is called a local maximum. So that's what we call as a local maximum. If f of AB is greater than or equal to f of xy on the domain of f, then f of AB is a global or absolute maximum of f. We similarly define a minimum, so we can do a picture for a minimum. So here's our set, and then our graph in 3D. Just do like a paraboloid or something. There's our point AB, and that's our point f of AB. All right, and then we got a point x comma y and f of x comma y, and that's going to be greater than or equal to f of AB. So let's go look at the second derivative test in Calculus 3. So the second derivative test, let f be a function continuous, let f be a continuous function of 2 variables, x and y, defined in a closed and bounded. So closed and bounded is another way of describing it. We call it compact region R in the xy plane. There is at least one point in R such that f takes on a minimum value, and at least one point in R such that f takes on a maximum value. So kind of like extreme value theorem and the second derivative test here for functions of 2 variables. So the procedure here is a little bit more complicated. So what you want to do is you want to locate all critical points of f on the region R. A critical number, a comma b, is in the domain of f such that the first partial with respect to x at AB is 0, and the first partial with respect to y of AB is equal to 0. Or at least one of the first partial of x or first partial of y doesn't exist. We'll only be looking at where the first partials of x and y evaluated at AB are equal to 0. And then we have a table here. And I have the critical points A, B, and C, and it just kind of depends. I think usually it's just described as the XY pair, but sometimes they communicate. They want to know the critical point also with the critical value, so sometimes the C is included. Okay, So your critical numbers, A, B, and then you set up this chart. So you have the second partial with respect to x, the second partial with respect to y, the mixed partial, and then we have this thing called D, which is equal to the product of the second partial of x with the second partial of y minus the square of the mixed partial. So if the second partial is positive at AB and the D is positive, then you can kind of think of that as your second derivative is positive at a critical number, so you have a minimum. Excuse me. If your second partial is negative and the D is positive, then you're going to have a maximum. Okay, and then just looking at D, if D is negative, then we have a saddle point. And if D is equal to 0, then it is inconclusive. You will need to check f of x, y on the boundary of the region R for extrema, just like checking the endpoints for f of x on the closed interval AB. So it's analogous to that. So we'll do some examples where it's just on the whole xy plane, and then we'll also do an example where we're on a closed and bounded set or compact set. We're going to do two examples in this video. Okay, so the first example says find all relative extrema and saddle points of the function f of x and y equals 4xy minus x to the fourth minus y to the fourth. And then I have the table set up already for everything, and there seems to be 3 rows, so possibly there's going to be 3 critical points here. All right. So let's go ahead and find the first partial derivative with respect to x, which is going to be 4y minus 4x cubed, and we want to know when that's equal to 0. Well, if you solve that for y, you have y is equal to x cubed. The first partial with respect to y is going to be 4x minus 4y cubed, and we want to know when that's equal to 0. That happens when x is equal to y cubed. So y is equal to x cubed and x is equal to y cubed. So replace the x with y cubed. So we have y cubed cubed. So y is equal to y to the 9th. If we subtract y, we have y to the 9th minus y is equal to 0. We can factor out a y, so we have y times the quantity, y to the 8th minus 1, which is equal to 0. Okay, then y to the 8th minus 1 is a difference of squares, so that'll factor into y to the 4th minus 1 times y to the 4th plus 1. That's going to be equal to 0. But y to the 4th minus 1 is a difference of squares, so that factors into y squared minus 1 and y squared plus 1, and then times y to the 4th plus 1, and that's equal to 0. But wait, y squared minus 1 is a difference of squares, so that factors into y minus 1 and y plus 1. Y squared plus 1 is a sum of squares, so that doesn't factor over the real numbers. Neither does y to the 4th plus 1. Okay, so the y values we get here is y is equal to 0. So if y is equal to 0, you have the relation you have the relation x is equal to y cubed. So x would be equal to 0 cubed, which is 0. So that gives us the critical point 0, 0. Next, y is equal to 1. And you have x is equal to y cubed, so x is equal to 1 cubed, so x is equal to 1. That gives us a second critical point of 1, 1. Okay, and then finally, we have y is equal to negative 1, and x is equal to y cubed, so negative 1 cubed would be negative 1, and that gives us the x fit there. And so it gives us our last critical point of negative 1, negative 1. Okay? So from here now we need to find the first partial with respect to x, second partial with respect to x, second partial with respect to y, and the mixed partial. Okay, so second partial with respect to x is going to be minus 12x squared. If we evaluate that at 0, 0, that's going to be 0. If you evaluate it at 1, 1, that's going to be minus 12. Likewise, if you evaluate that at minus 1, minus 1, it's going to be minus 12. The second partial with respect to y is going to be negative 12y squared. And so it's essentially going to be the same thing when we evaluate this at 0, 0, it's 0. Evaluate it at 1, 1, it's going to be minus 12. And evaluate it at minus 1, minus 1, it's going to be minus 12. Okay. Lastly, we need to find the mixed partial. So first partial with respect to x and then y. That's just going to be 4. So it doesn't matter what x or y is, it's just constantly 4. Okay. Alright, so now we're going to find d. So first for 0, 0 is going to be 0 times 0 minus 4 squared. So it's going to be negative 16, so the d is negative. Our conclusion is that's going to be a saddle point. Next one we're going to do is minus 12, that's for the 0.11, and then minus 4 squared. So it's going to be 128. So your second partial with respect to x is negative, but the d is positive, so that's going to tell us that we have a maximum point. And we're going to have the exact same thing happen at the point minus 1, minus 1. That's also a maximum. Okay. If we wanted to find the z values, then we would evaluate at these. So the saddle point, if we evaluate this at 0, 0, it's going to be 4 times 0 times 0 minus 0 to the 4th minus 0 to the 4th, so that's going to be 0. So our saddle point is going to be at 0, 0, 0. Okay, if we want to find the maximum at 1, 1, it's going to be 4 times 1 times 1 minus 1 to the 4th minus 1 to the 4th, so that should be 2. So then we're going to have a maximum point at 1, 1, 2. And finally we'll find f of the point negative 1, negative 1. And so we're going to have 4 times negative 1 times negative 1 minus negative 1 to the 4th minus negative 1 to the 4th. And so that's also going to be a 2. And so we have another maximum point at the at minus 1, minus 1, 2. Okay. And you can kind of see the graph here. Kind of looks like either Batman or a cat or something like that. So you do have your saddle point here, and then you have your 2 maximums right here and here. So those would be the points of the cat's ears, or the tips of the hat for Batman. Okay, I got one more example in this video, so let's go ahead and take a look at it. So we're going to look at finding the same thing as the previous one, find all relative extrema and saddle points of the function f of x, y is equal to 1/3 x cubed minus 2/3 y cubed plus 1/2 x squared minus 6x plus 32y and then plus 4. So we're going to start it out by finding the first partial with respect to x, which is going to be x squared plus x minus 6. And we want to know when that's equal to 0. Well, this factors into x plus 3 and x minus 2. So then our solutions there would be x is equal to negative 3 or x is equal to 2. So we'll go ahead and put those two x values on and see what we get for the y. So first partial with respect to y, it's going to be negative 2y squared plus 32, and that's going to be equal to 0. So we can factor out a negative 2, we have y squared minus 16 is equal to 0. So negative 2, and then difference of squares, y minus 4, y plus 4. So that's going to give us y is equal to 4, or y is equal to negative 4. So we need to pair the negative 3 with both 4 and negative 4, and also the 2 with 4 and negative 4. Okay. So there they are paired with 4, and then we'll pair them with a negative 4. So that gives us 4 critical values. Okay. Now we need to find the second partials with respect to x and y, and also the mixed partial. So the second partial with respect to x. It'll be 2x plus 1. Okay, so if we evaluate that at the point -3, 4, it's going to be -5. Evaluate that at the point 2, 4, it's going to be +5. Evaluate that at -3 and -4, it's going to be -5. And one more time at 2 and -4, and that's going to give us 5. Okay. Now we're going to find the second partial with respect to y. Okay, which is going to be -4y. So evaluate that at -3 and 4, that's going to give us -16. Evaluate it at 2, 4, it's going to give us 16. At -3, -4 is going to give us +16, and one more at 2, -4 is going to give us +16. Let's find the mixed partial derivative, second partial derivative. And that's going to be 0. Okay, so then that means it doesn't matter what the point is, it's mixed partial is always 0. Okay, now we can go ahead and calculate the d. So -5 times -16 minus 0 squared is going to be 80. So the d is positive, and the second partial with respect to x is negative, so we're going to have a maximum in there. Moving on to the next one, 5 times -16 minus 0 squared, it's going to be -80. Okay, and so that is going to be a saddle point because the d value is negative, so we got a saddle. -5 and 16, -5 times 16, at the point -3, -4, minus 0 squared, that's going to also give us -80, so we get another saddle point. Okay, and finally, the 0.24, our values are going to be 5 times 16 minus 0 squared, so it's going to be 80. And so we're going to have another maximum, this one's going to be a minimum point because of the second partial with respect to x is positive. So we're going to have a minimum there. Okay, all right, and then if we want to find the z values in f of -3, 4, that is going to be 103, and that's going to be a maximum. At -3, 4, and 103. F evaluated at 2 and 4. It'll be 82, and that's going to be a saddle at 2, 4, and 82. F of -3 and -4. Be -68. That's also a saddle. At -3, -4, and -68. And finally, f of 2, -4. That's going to be -89, and that's going to be a location of a minimum at 2, 4, -4, and -89. Okay, now I've tried graphing this in GeoGebra 3D, and I can't get a good look at it. So maybe there's some graphing software out there that I'm just not familiar with that be able to generate this figure, and we can actually see the saddles and the mins and the maxes a little bit nicer. But anyways, so that is it for this video. I think I have 1 or 2 more for this section. It's a little bit longer than maybe what we did last week. Okay, so we'll see you next time.